Okay, so the best way to proceed is to take a specific example. So the first example, I'll use the same differential equation as in the previous podcast. So that is going to be y double prime plus 4 times y prime plus 3y. So previously we solved that equal to 0, but now we're going to solve it equal to 3x plus 4 plus 4e to the minus x. Okay, so that's the problem we're going to solve. We've already done this, so just to remind ourselves, we've got the auxiliary equation y double prime gives you lambda squared plus 4 lambda plus 3 equals 0. So that you can solve, you get lambda is minus 1, lambda is minus 3. So y CF is c1 e to the minus x plus c2 e to the minus 3x. Okay, now that's the first step. We've got the complementary function. The second step is we make a guess for ypi. Ypi, the particular integral, is, well, we've got a polynomial, first degree polynomial. So let's write down the most general first degree polynomial, ax plus b. We've got an exponential, e to the minus x. So let's write down the most general exponential of the same form. And then alarm bells start ringing, because that is in the complementary function. So what does that mean? That means that if you look at your complementary function, this e to the minus x here is the same as that e to the minus x there. So this thing as it stands, if we were to choose c1 equals 1, c2 equals 0, we would have ycf is equal to e to the minus x, which is the same as that. Okay, so that's when you say this isn't going to work, and what you should do instead is take this and multiply it by x. Okay, so we need to multiply by x. So instead of our d e to the minus x, we have dx e to the minus x. So we don't touch the rest of it. We leave that ax plus b alone, but that d e to the minus x becomes dx e to the minus x. Now, supposing you didn't notice that this was in the complementary function, what would happen? Well, you'd put it in and you'd find that d would vanish. And if you are solving any of these problems and you do find that one of these constants here, whose value you're supposed to determine, has disappeared, then probably what's happened is it was in the complementary function. And the thing to do is to go back and take the part that's disappeared, multiply it by x, and hope for the best. See if that works. So I will write down dx e to the minus x, and we will proceed. Okay? So there's our guess for our particular integral. Now this is supposed to be a solution of this equation, y double prime plus 4y prime plus 3y equals 3x plus 4 plus 4e to the minus x. If it's going to be a solution of that equation, we're going to have to find the values of a, b, and d that make it work. So to do that, we substitute that into the equation. So we need the first and second derivative of this function. So ypi prime, we've got an ax, derivative of that is a, derivative of b is 0, that's how it vanishes. And then we've got a dx e to the minus x. We bring out our trusty product rule. So that becomes d times the derivative of x, which is 1, times e to the minus x. So it's d e to the minus x plus dx times the derivative of e to the minus x. So it is dx times minus e to the minus x. We need the second derivative, ypi double prime. The derivative of a is a constant, so that vanishes. Here we've got d e to the minus x, so derivative of that is minus d e to the minus x. Here we have x times minus e to the minus x. Differentiate that, so differentiating the x first gives us a minus d e to the minus x, so this actually becomes minus 2d e to the minus x. And then we're left with, here we'd take x times the derivative of e to the minus e to the minus x, which is plus e to the minus x. So it is dx e to the minus x. We now substitute y double prime into that part of the equation, y prime into there, y into there, and we try to find a, b, and d that work. So we've got minus 2d e to the minus x plus dx e to the minus x. That is our y double prime. Plus 4 times y prime. A plus d e to the minus x minus dx e to the minus x plus 3 times y. So it is 3 times ax plus b plus dx e to the minus x. And all of this is equal to 3x plus 4 e to the minus x. 3x plus 4 e to the minus x. Now, what we have to do is we have to find values of a, b, and d for which this works. And it works not just for any value of x, or not for just for some particular value of x, but for any value of x. And the only way that you can have two functions being the same for all values of x is if every part of the function is the same on the left and the right. So we can collect all our terms. So let's do that. How many e to the minus x's do we have? We've got a minus 2d here. We've got a dx e to the minus x. We've got a minus 4 dx e to the minus x. And we've got a plus 3 dx e to the minus x's. So those ones vanish. Well, that's convenient because we don't have any x e to the minus x's on the right-hand side for them to be matched with. So we don't have any dx e to the minus x's. We do, however, have 4d e to the minus x from there. So 4d e to the minus x. So that we've dealt with that term, and that term, and that term, and that term, and that term. So what's left? We've got 4a and 3ax and 3b. So we've got plus 3ax plus 4a plus 3b, and that is supposed to be equal to 3x plus 4 e to the minus x. So if these things are going to be equal, and not just equal, but equal for every value of x, then the exponential term over here on the left has to be exactly the same as the exponential term on the right. The term that's linear in x over here on the left has to be exactly the same as the term that's linear in x on the right. And the term that's constant on the left has to be exactly the same as the term that's constant on the right. In that case, we get minus 2d plus 4d, so that is 2d is equal to this coefficient, which is 4. So d equals 2. We get 3ax is equal to 3x. So 3a is equal to 3, or a equals 1. And the last one is 4a plus 3b is equal to 4. But a we've just decided is 1. So this is 4 plus 3b is equal to 4. So 3b is 0, or b is 0. Okay, so we've now worked out the values of a, b, and d that make this guess here a solution of that equation. So I'll erase the intermediate lines, and I will substitute those values in. So let's put d equals 2. There we are, there's d. I'll replace it with a 2. A was equal to 1, so that's easy. We'll just erase the a. And b was equal to 0, so that's also easy. We can just erase the b. So we get our solution here, ypi, is equal to x plus 2x e to the minus x. And that is the function that works in that you substitute that ypi into the left-hand side of the equation, y double prime plus 4y prime plus 3y. And what it gives you is the right-hand side of the equation. So the last step of the process of getting the general solution of this example is to take your particular integral and your complementary function and you add them together. This is a feature of linear equations. If you have a solution to the homogeneous problem and a solution to the inhomogeneous problem, then the sum of these things is also a solution of the inhomogeneous problem. So the general solution is y is ypi plus ycf. So y is x plus 2x e to the minus x plus the complementary function in this case, which was up here, c1 e to the minus x plus c2 e to the minus 3x. There's our general solution. Now in this problem, I haven't given you any initial conditions or boundary conditions. If I had, we would use those to work out the values of c1 and c2.